Frank and Charles and Gloria and I were chatting. We thought it would be good to get together with you all and UMass people that are working on this project to kind of give you a sense of where we are with things and to give you some periodic updates. So there's going to be a lot of stuff here to share with y'all, and I'm hoping that we can leave plenty of time for questions, inquiries, feedback, suggestions, as we introduce some of this material to you all. So with that, I'll go ahead and get started. You can still see my screen okay?
Yes.
Awesome. Thank you. So there's a bunch of new faces that for the people that have been involved in this particular saltwater intrusion project on the Zoom call. And so I'll introduce the project team, and it's a really great group of young researchers who are collaboratively working with myself on this particular problem. We'll discuss some of the new advances in the geologic model, the hydrogeologic modeling that we've been doing, and then get into some details of what we've discovered and found out with respect to the probability and vulnerability of the Plymouth Carver aquifer to saltwater intrusion. And then, like I said, I'm hoping to have plenty of time to have questions and discussions. So many of you here know me already, and I was just discussing before some of you joined. We do a lot of different work around the state and the world on issues relating the interactions between freshwater and saltwater, and particularly interested in this project, really pushing the scientific understanding of how certain parts of our planet are going to respond to not only climate variability in terms of the amount of water that comes into aquifers, but also particular issues associated with coastal change and sea level rise. And so the other members are going to team. If you could just go ahead and unmute yourself when I call your name, you can just give a quick introduction here, and then you'll hear from some of them as some of the things that they've been working on come up. And I guess I'll start with Brendan, who is here. Well, he's in Amherst, but I think he's in Oregon or something. I don't know where you are. But...
Yeah, I'm in Washington State. Yeah.
Washington, yeah.
Yeah. Hey, I'm Brendan Moran. I just received my PhD with Dave last year. I've been working with Dave since 2016. Got my master's at UMass and then my PhD. I've been involved in some of these projects over the years, mainly working on the hydroclimate aspects, the recharge, and climate variability. So I'm contributing in that way to this team, and I'm happy to be here. Thanks.
Thank you, Brendan. Dan.
Hey everybody, I'm Dan Corcoran. I'm a graduate student working with Dave, and prior to coming to UMass, I worked as an environmental consultant, focusing on groundwater modeling and freshwater saltwater interactions.
Thanks, Dan. Xander.
Hello, everyone. My name is Xander. I graduated from UMass from my undergraduate about a year ago, and I've been working with the team as a research technician full-time since. I just kind of help out on a bunch of different projects.
Thanks, Xander. And Carly.
Hi, I'm Carly. I am in the one-year hydro program at UMass, and I am currently working on a groundwater modeling project that will show the interface of fresh groundwater and salty ocean water and how that interface will change over time due to saltwater intrusion.
Thanks, Carly. So as you can see, it's a very UMass heavy team, and it's great to have this brain trust of people that are contributing to this project. So just to kind of revisit where we're going, the main focus of our work here is to assess the impacts of saltwater intrusion and into the freshwater aquifer and connected water bodies of the Plymouth Carver aquifer, really focusing in the town of Plymouth, as you'll see in some of the forthcoming images. And the way that we're doing this, there's lots of different approaches towards kind of assessing these changes. The way that we've built this program out is through the use of numerical models that will help us predict, assess, and determine potential vulnerabilities of these freshwater aquifer systems to sea level rise and associated coastal change. So just a brief kind of project roadmap. We've completed some of our initial saltwater intrusion assessment using what we know about the position of the water table with respect to the land surface. We've, as you'll see today, we'll talk about both of these things today, have built a new model domain structure and boundaries for the Plymouth portion of the Plymouth Carver aquifer. And Xander will go through some of those details. We're in the middle of finalizing some of the density dependent groundwater models that we'll use to make assessments of different scenarios of both terrestrial changes and hydroclimate. And what I mean by that is changes in precipitation and how changes in that will potentially lead to water level or water table response to things that are happening terrestrially, and then that combined with changes in sea level associated with different climate scenarios, and Brendan will talk a little bit about that. And obviously all of this needs to be wrapped up by June of 2023. And I think, through maybe in the discussions with you all, we can have some additional iterations on kind of how we wrap this up and the kind of the transfer of some of the knowledge from what we've learned here. I see there's something in the chat. Is that for me or is that for somebody else? I'm not sure. Charles, do you mind keeping an eye on that? Are you there?
It had to do with some Wi-Fi connection issues.
Okay. All right. So where we are, we've and I kind of went through that already in terms of our roadmap, kind of assessed possible location of the freshwater surface water interface in the region, refined the existing hydrogeologic model of the aquifer system, and have developed the boundary conditions and structure for the groundwater flow model. Where we're really focused on in the next 6 to 7 months, one of the really key things I think within this project is really to understand how some of the coastal water features are going to respond to changes in sea level. They're going to be the most vulnerable parts of the hydrologic system in terms of responding more quickly to changes, responding to storm surge, event-driven changes in ocean levels associated with nor'easters and other large tropical systems. Part of that will be looking at how the aquifer system responds to sea level rise and the kind of combined response associated with changes in the hydrology of the system. And then I think one of the most important things is really to provide the town and you all with recommendations and some actionable things that you can do to, you know, plan into the future. Because after all, you know, this grant is really to kind of provide some understanding that will help with future planning in terms of, you know, climate change. So just overall, you know, where we are aiming towards, kind of our target is, I think, an updated or a revised 2022, 2023 updated groundwater flow model that really simulates better the freshwater, surface water interactions of coastal water bodies. Because as I'll talk about in a second, the existing model for the watershed is lacking in that regard. And Brendan will speak to this, but incorporating sea level rise scenarios into you know, into these aquifer models, and then to make some predictions and assessments of where we think some of the more significant changes might occur on the coastline, and then some strategies and assessment or strategies and recommendations moving forward. So the Plymouth Carver aquifer, the Plymouth Carver, Kingston, Duxbury, depending on, you know, the geography, but is a really interesting system. It's very unique. It's a very permeable aquifer that is strongly connected to the surface water bodies of the system. There are, you know, very few streams and rivers in kind of the normal sense of that word, and meaning that most of the aquifer is really connected very strongly to you know, to the surface water bodies. And this has been known for a long time, and one of the really interesting aspects of the system, and this was some work that was done in the previous model, where that work showed the contributing areas of different hydrologic features on the landscape to groundwater. Essentially, what I'm going to show you in a map, and a lot of you have seen this already, is predictions of, like, if you have a pumping well and you pump water out of the ground here, what is the kind of the surface footprint of where the water that came into the system that was pumped at the well, where did it come from? Okay. And so this representation of this polygon here really reflects the position of the water table at the surface at this location. So here, this map that I'm showing you with all the bright colors reflects the zones of contribution to different different receptors. And so what I really want to, the important thing I want to show you here is all of these areas in orange along the coast. These are areas where when precipitation occurs, when rain falls or when snow melts and it infiltrates into the aquifer, those are parts of the aquifer, the aerial landscape, where the water will come into the ground and go right out to the coast. Okay, and this is called the end point of that is called what we refer to as submarine groundwater discharge. Essentially, this water is coming in terrestrially and is not interacting with any surface. It's not going into stream.
Mentioned earlier, and basically, and in purple you can see that is the revised domain for the model for our study, and the color map is the water table elevation calculated from that previous model, so the Masterson 2009 model. So what we did is, you can kind of start animating the slide, Dave. So what we did is we identified the groundwater divide, and as Dave mentioned, we're really focusing on the coast. So we're looking at everything east of the groundwater divide, kind of shown with those purple arrows, and then we kind of made our domain cut through that divide, and then since our model really needs to focus on how changes in ocean levels may impact saltwater intrusion, we need to include the coast, so we extended the domain 10 kilometers offshore. Yeah, so we can go to
Yeah, and I'll just add a few things, Xander, too, is this helps a lot cut down on computation and complexity, because what left of this line here, kind of to this side, this water flows into Buzzards Bay and down into these drainages. So we're really leveraging the predictions or the assessment that was done in the Masterson model to allow us to kind of define this divide, and the assumption, and this is supported by some new work that came out a few years ago, is that, you know, the position of this divide, people have think that this has been this way for thousands of years in terms of the kind of the groundwater mound, and even with changes in recharge, we expect or changes in climate, we expect that this divide will more or less be where it is, you know, within the domain of our modeling out to 100 or a couple hundred years.
Yep, and then so that kind of is how we define the lateral extent of our model. And now I'm going to go into how we define the top boundary. So you can see in purple, that is the extent that I just described earlier, just so we can know where we're at. And you can see on the left side, in the kind of the blue and the green color map, that's a digital elevation map. So you can animate this, Dave. Over on the left is the new DEM from 2022 from Mass GIS. And on the right side is Cape Cod bathymetry map. And we merged these two data sets into the final top boundary of our model, which can be seen right there. So that's the merging of the land surface elevation raster and the bathymetry raster data set.
So this map, it looks very extreme. It has like 20 times vertical exaggeration, which means we've stretched it 20 times to make it look more interesting.
Yeah.
What's really cool about this is we have now a kind of a surface that allows us to define what that offshore topography is, bathymetry, along with the land surface, the onshore bathymetry, then to really capture some of the dynamics that occur as freshwater and saltwater mix and interact in the ground.
Yep. And then now I'm going to go over kind of the updated bottom boundary, or kind of the bedrock elevation, where we're assuming that there's no water flow. And one of the really nice things about this new model is that we have this new sediment thickness data set, and a lot of that sediment thickness data comes from this horizontal to vertical spectral ratio data. And basically what that means is you take you put an instrument on the ground, a seismometer that records vibrations in the ground in 3 directions, so east, west, north, south, and up and down. And basically you can just process this data to understand sediment thickness. And I'd be happy to go into this further if anyone has any questions, but I feel like that's a good intro for now. Here's an image of, I think that's Steve maybe collecting some data using that instrument I just mentioned. And the plot on the right is kind of the final plot you can get after processing the data, and you can take that frequency of where that spike is on the x-axis and plug that into an equation that has been made for kind of the Massachusetts area in particular, and you can find a overburden thickness or a depth to bedrock. So that, and then, yeah, here are some other images of.
It's a lot of sitting around, as you can tell.
Yeah, you record for 30 minutes, so you're sitting for at least 30 minutes.
Yeah, but what's cool, and Xander, I'll just talk about this quickly, is
Yeah.
So Steve Maybe, who Xander mentioned, is the state geologist in Massachusetts, and they've had this program to go out and collect data all over the state. And we combined forces this last May and collected all those new data points in the triangles all across the aquifer. And as you could see, all these different points here are areas where we had either existing borehole control, where we had boreholes that penetrated bedrock. And in the Plymouth Carver, wasn't a lot of data because it's really thick and people don't typically drill to bedrock. And so we actually put this grid out. Steve maybe and some of the students, some of his interns over the summer collected all those new data points to populate the depth to bedrock of the region. I don't know, Xander, do you have anything?
No, yeah, I just think it's just a cool geophysical tool that can fill in gaps in overburden thickness where you don't have any cores. And yeah.
So and this is a sneak preview. Not many people have seen this map. This is a brand new map of the bedrock elevation across the state. We haven't had a product like this. There's actually not many states that have this product. So what this is it's a map that doesn't show the topography, but it shows the elevation of rock across the Commonwealth. And so our project contributed, and obviously is focused down here. But we have this really nice data set now across the state that allows us to really define, primarily in most circumstances, most groundwater flows through the unconsolidated glacial sediments on top of the bedrock. So it's a really nice product that we have now. All right, Xander, I'll let it back to you.
Sweet. So that's kind of some crucial new data that we have for the bottom boundary. So here on the left side, in that kind of brown to green color map, you can see that's the new depth to bedrock map we were talking about. And from that, we calculated a bedrock elevation on land, and we combined that with the, you can see there's a contour map where the ocean is, and that's a bedrock elevation map from Stone and Stone 2019 report. And so we basically merged those two data sets to get a final bottom boundary where we're assuming there's no flow.
Yeah. So one of the things, and we've talked about this and have had circulated some of these products around. So there's been a bunch of seismic reflection surveys offshore that have imaged the glacial sediments in Cape Cod Bay. So we've taken that information and where the interpreted depth to bedrock is offshore, merged that with the onshore data to kind of create a seamless bedrock surface that goes offshore. So this is, at least I'm not really aware of this in many places where we've got now kind of an onshore offshore bedrock topographic data set. But it's critical because this is the aquifer offshore in the sediments that's connected to the onshore aquifer. So we needed to really know where that is.
Yep. And so there is the final kind of seamless raster that Dave just mentioned.
Yeah. And one thing that you can see, it's pretty apparent, is we don't have as much information offshore. So it's much more smooth, than the onshore. Some of these like these visualizations and things like that. Oops, let me just go back. Kind of lend themselves to some really nice images and things like that you guys, we can share and generate for, for publicity or whatever, I think that'll be nice. So yeah, as Xander said, that this kind of blue solid object, now we have it full 3D, we know where everything is, and that defines the aquifer.
Yep.
All right, Xander, I'll let you go.
Cool. So now this is the same. What we're looking at now is we brought the 3D aquifer that we just looked at into another software, and so now I'm going to talk about the hydrogeologic model. So we're basically looking at the same aquifer. So I'm going to go over the boundary conditions of this model. So kind of the key things
Xander, just let me interject quickly.
Yeah.
The boundary conditions and kind of the vernacular are how we tell the model like what is where and what is connected, like where are rivers and where are ponds, where are the oceans, all the different elements that go into making predictions and building the fundamental hydrologic elements that make these systems, or how these systems work.
Yep. So here you can see the rivers, and they're defined using a drain package in ModFlow, and then you can just keep
low permeability. And I think some of these locations and the size of them might change as we refine the bedrock surface map or elevation map.
Yep.
And like this is an outcrop in the bay. So we're not simulating flow within that domain. And in the Masterson model, they simulated flow in the bedrock. And it's something that, you know, it's kind of in progress whether or not we'll make those cells active or not. They're giving us a hard time numerically. So as Peter knows, some of these models are finicky.
Yep, and here is so here's the steady state version of the model. And so you can see in the color map, that is basically the water table elevation. In this current version of the model, about 44%. So in this version of the model, there's about 630 meters cubed per day of water coming into the model. And of that 630,000 meters cubed per day, 44% of that water is leaving the model via discharge to streams. And the other 56% is leaving to the ocean via submarine groundwater discharge, which is what Dave was talking about earlier.
Yeah, and I would, for this part of the model domain, it's fairly similar to what the Masterson model projected. And I think the thing to remember about that is, you know, most of this domain, a lot of this domain has those recharge areas that are contributing right to the coast. I showed you earlier.
Yep, and then the next image is gonna show the cells in the model that do discharge water to the coast. So,
So what you're looking at here, to take a little explanation, and Dan, if I get this wrong, correct me, but these are cells in the model that you actually have water going to the coast. So it would be part of the domain that projected to the surface where water's flowing, you know, right to the ocean out of those cells, or right to the bay.
Yes, those are the locations in the model domain where the model is indicating submarine groundwater discharge.
Right. It's not the same as those contributing areas that I showed you before. The contributing areas for those cells would be, you know, a big part of the model domain. And I'm hoping we'll have some of those revised maps for this model domain that'll show those contributing areas.
Yep.
Okay.
Yeah.
I think this is Brendan.
Yeah. I think there was quickly, I think Peter had a.
Yeah,
question
Peter,
in the
what's
chat.
up?
Hi there, guys. This is great. I got to say, David, it's really wonderful to see the work that you guys have put in, especially the seismic. That was a complete surprise, and new data, which is really, really wonderful. Can you talk a little bit about the current, like the size of the resolution of the model grid and the layering? Like, how many layers are you using?
Yeah. Right. I'll let Xander handle that. What's the horizontal?
So right now it's 100 meter grid size, and it's a 4-layer model.
Four vertical
Layers, exactly.
discretization layers, yeah. And one of the things I think we're finding out is that we could probably remove a large chunk of the domain offshore.
Yeah,
You know, I mean, until we get the full density dependent model spun up, we'll, we don't really know where we can cut it, but we wanted to be conservative and push it out.
Mm.
I mean, off of the south of South Carolina, off of New Jersey, off of Long Island Sound, you see submarine groundwater discharge that can extend more than 5 kilometers offshore. So we wanted to be conservative of that. So that I'm hoping we can we can pull that boundary in perhaps closer to the coast, and then refine the model more than we have right now.
I was gonna ask how long it takes to run, but apparently the machine that maybe it's running on is a slow machine, so maybe it's not a good question.
Yeah, well, it's, with these things, it's like I forget what the word is, but you always are pushing, right, to like how many, what's the max number of cells that you can you can have in your model. So it's just, you're always running up against those computational limits. But what we've been talking about, we have a green high performance computing center here in Holyoke that's run by hydropower at the dam that UMass is part of, and we've been thinking about if we have to, we can put some of these simulations on that. It'll run a lot faster on that cluster. But
Thank you.
yeah, thanks, Peter. All right, Brendan, I think you're up.
Yeah. Okay. Yeah, so I'm just gonna quickly go over some of the forcings for hydroclimate changes and also sea level rise that are gonna sort of drive the model to assess how sea level rise and climate changes will affect water tables and stuff like that. So this is so the Guyman-Hertzberger relation is a sort of simple way to estimate the depth to seawater in an aquifer. So we took the Masterson predicted heads on the right there, and we applied this this function. So it's essentially 40 times the sea level, or the water table above sea level is where you expect the depth to seawater to be. And as you can see over on the right here, a lot of them the depths are pretty deep. So it just sort of illustrates, there's probably the sea level is, not close to the aquifer in a lot of places. It's quite deep. Along the coast, there's some areas that probably, can get closer. And like Dave was saying, those water tables may be slightly higher than we think they are. So maybe the sea level is a little bit closer than this illustrates. But if you take those estimates and you take the superficial alluvial aquifer on the right here, this sort of raster beneath the domain, and you see it, is that sea level predicted to be within the aquifer, the alluvial aquifer? And you can see here that actually there's some arrows, Dave, if you click the animation. You can see here that those are the only places where we expect any seawater to be within the aquifer. So very small, potential areas. There could be some, if it's kind of slightly closer, there could be some other areas, but it's actually, not much. It's probably the aquifer. The sea level is probably within the bedrock in most places.
Yeah. So what we're seeing here, we're trying to figure out where is the salt water within the alluvial aquifer, and because of the thickness of the alluvial aquifer and the depth to that interface, there's very limited, essentially all of the alluvial aquifer has fresh water in it is essentially our assessment. That doesn't mean that under, sea level rise or perhaps, some pumping changes associated with freshwater extraction wells that you can't, cause that saltwater interface to migrate inland.
Yeah, so Peter has a question there. Yeah, we used the Masterson predicted water levels for this. But a lot of these are quite deep, even along the coast.
Yeah,
So
I mean,
you could see 500 feet.
Yeah, it's a little silly because
Yeah.
it's like because of that scaling of 40, there's the depth to the saltwater is 40 meters or whatever per 1 meter of head here. So you have 100 meters, it's 4,000. So
yeah,
this was just something that was part of the kind of original scope, and so we wanted to make sure to follow through on that. All right, Brendan, I'll let you talk a little bit about the hydrology.
Yeah, just quickly. So we took that the average recharge per year based on the Masterson a number, which is 686 per year over the aquifer, and we transformed it with this function. So the P minus PET. This is a very generalized plot on the left here, but it gives you a sense for the variation in groundwater recharge over the year, and we applied that to get a monthly time series of total recharge in the aquifer to use in the model. And yeah, so as you can see on the bottom left here, we have this well, which is just to the west of the model domain. If you actually animate it, you can see what so there's that, and then so you can see that in October through April, you get, and this is generalized, it varies season to season, but we're talking about on average a recharge scenario or recharge driver. And so you can see that, you get recharge through from April to October to April, and then May through September is generally net loss of water, so not actual recharge to the aquifer, and that's what we assume here. And and on the right here, there's another plot just from data from the Douglas and Kirshen report that shows this in northern Massachusetts, but it's the same sort of climate regime. So that's what we've used here, and this is the baseline. This isn't a scenario, but if you go to the next slide, we can.
Yeah, I just want to make sure people understand.
Yeah.
When we talk about recharge, we're talking about the amount of precipitation that becomes groundwater. So it's like how much water that has fallen out of the sky actually makes it into the aquifer, as opposed to water that gets used by plants and trees or evaporate. So it's a key input into the model.
And then so these are the climate change scenarios from the DeCanto sea level rise report, and we're essentially going to use these likely range numbers here from the RCP 2.6 through 8.5 as the high end, and and this will drive the model to simulate sea level rise over through 2100 is the plan right now, but we could go to 2200 potentially.
And one of the things that you have to be careful with these plots, or this confused me when I was looking at
the rate of change.
These are rates. So the sea level is supposed to be the rates of increase, and even once we hit 2100, the rates will stay steady, but each year we'll be adding 30 millimeters a year to sea level at that point, in the most extreme. And this doesn't even account for the full loss of certain parts of Antarctic ice sheet, which would make it worse. Peter, I see your hand up. Is that
Yeah, this is just another element of the water budget that would come out of climate change. Are you guys going to look at how warming would increase evapotranspiration and therefore reduce recharge and therefore reduce the water table or bring down the water table some? That seems like an often overlooked element of climate change that can affect the model.
You're right. Right. So another slide, the next slide actually would talk about just changes in recharge seasonally, which probably capture a lot of that variation, in terms of the wet season or the winter contributing less overall to, be partially because of snow, changes. And so that the P minus PET there probably captures some of that, but actually, discretizing the ET to change, I'm not sure we've talked about doing that directly.
Yeah, I don't know if, one of the things is, in models like this where we kind of we take kind of what's left over after the, Peter, right, after it's made it through the the soil profile and into the unsaturated zone. Perhaps we can consider a scenario where we look at like reductions in recharge or the same or increase in recharge and just try to bound those possibilities. I think it's
I can see that you've got some shifts in the precipitation pattern, and I just think it's worth mentioning at minimum so that people are aware that changes in temperature will have an effect on changes in recharge. Whether you do it as part of this report or you hold it out as something that you might look at in a future analysis.
It's we were talking about this a few weeks back about how to really capture the range of possibilities. The other thing that we need to be thinking about are some of these larger scale droughts, like the one we had this last year, or 2016, 2020, we can name off a bunch, and trying to put in some of that interannual variability, and that's I'm hoping we could get to the point where we have enough resources left to kind of look at some of those scenarios, because I think that would be really interesting. Most of the parts of the world that are doing this type of work often just kind of look at the sea level rise and really haven't explored the kind of the terrestrial to from the terrestrial hydrology to the coastal and those connections, because I think they're important.
Definitely. So we right now we're thinking we would simulate a wetter scenario and a drier scenario overall, and then also probably a shift in seasonality of recharge.
We're seeing, we're doing some other work with the state right now, and one of the things that our growing season is getting longer. You probably all saw this if you were in Massachusetts this November, right? So as that growing season gets longer, you're changing your water balance, and
people are going to pump more water to irrigate for longer time.
I still have peppers. I was picking a few weeks back. So
so sort of along those pumping scenario lines, we were thinking we would, based on these projections from the Douglas and Christian report, we could simulate changes in water and pumping over this time frame too. We could, so those are sort of the drivers here from a scenario perspective, and
that's something where I think it would be good to leverage some of the volunteers if we have the capacity to maybe dig in and think a little bit more about, what could some of the, what is the town of Plymouth planning for, how does that compare to what Masterson used in their study in terms of water usage and water consumption going into the future.
Yeah. We can. So these are sort of a framework, all of these, and we're going to adjust based on throughout this work. So yeah.
Awesome, Brendan. Thanks. I think we just have a few more slides, and we put some of these in here for Frank, because Frank had some questions for Dan, and we just wanted to, maybe Dan, go ahead, take it away if you want.
Sure, I can kind of discuss this. And Dave kind of touched on this earlier, but submarine groundwater discharge it occurs in pretty much any coastal aquifer. It's where fresh groundwater discharges to the ocean through the seafloor. And the reason why this occurs is because the hydraulic head, which is to say the pressure of the fresh water in the aquifer, is greater than the pressure of the saline groundwater. And so essentially when it's just a push and pull type dynamic. And when you have more pressure in the fresh groundwater aquifer, it pushes itself out offshore and discharges to the ocean. So what can affect this pressure balance? Sea level rise will increase the pressure in the saline groundwater, and groundwater pumping or any kind of reduction in aquifer recharge will reduce pressure in the fresh groundwater aquifer, and any of those things, if they occur, will result in a reduction in the amount of submarine groundwater discharge. We can go to the next slide. And Dave already showed these figures a little bit earlier, but what we found in the Plymouth Carver aquifer is that submarine groundwater discharge occurs pretty much along the entire coast and aquifer system, except with the exception of a few spots where there's outcrop along the shoreline, bedrock outcrops along the shoreline. Where this submarine groundwater discharges occurs, we did show a figure earlier of our steady state model. That's also a homogeneous aquifer model. It's going to occur anywhere from near shore to, like Dave was saying earlier, it can be kilometers offshore. And one of the things that can really impact that is heterogeneity in the subsurface. So you have a confining hydrogeologic unit that prevents groundwater flow that can result in submarine groundwater discharge further offshore. But the key takeaway is that submarine groundwater discharge and saltwater intrusion are linked. So that pressure balance that I described before, it not only affects submarine groundwater discharge, but it also affects saltwater intrusion. So those same, so while submarine groundwater discharge is an indicator of where we would expect to see more or less saltwater intrusion, it's actually just being controlled by the same pressure balance.
All right, and I see there's maybe a new chat there, but we're gonna stop. And Charles, you can go ahead and pause, stop recording. I remember to tell you to stop, not start, but